We're now going to talk about limits involving infinity. And there's actually two different types of limits that involve infinity. There's limits as x goes to infinity, and then the function like maybe levels off at a certain value. And then there's limits that actually go to infinity. Okay, and those are two different types of limits. So let me start with this. We want the limit as x goes to infinity. So this is a limit as x goes to infinity. So we have an infinity here. So the limit as x goes to infinity of f of x minus 1 over 2x plus 6. Now one of the really cool things is, let's write this down. For limits as x goes to infinity, you can use the same rules as regular limits. For limits as x goes to infinity, the same rules for regular limits apply. Okay, so that's cool. We can use the rules we already know. So one thing to keep in mind is the following, that the behavior of a graph like y equals 1 over x, right? A graph like this is actually leveling off here. It's actually going to 0. Okay, so if you have a constant on top here and you have any x value increasing, it's just gonna, the bottoms, you're gonna be dividing by a bigger and bigger number, and it's just going to level out to 0. So any constant over an increasing function is gonna go to 0. Okay. Now here you don't have a constant, right? What you have is a linear function, and then the bottom is also a linear function. Okay, they both are linear functions. So what's going to happen in this case? Well, there's a strategy here that you can use, and that is with rational functions like this and with some other functions as well, you can multiply the top and bottom by the largest degree that's in the denominator. Okay, and not the largest degree, but by 1 over the largest degree. So let me show you what I mean. Okay, the denominator is a linear term. That's the largest degree. And so I'm going to multiply the top and bottom by 1 over x. That's not going to change the value of the function, of course, because it's like multiplying the top and bottom by the same thing is like multiplying by 1, right? So now as I go take the limit as x goes to infinity, what I can do is distribute the 1 over x. And let me show you what happens here. So when I distribute it over the 5x, the x's cancel out, and I'm just left with 5. And then I got minus 1 over x. So that'll be my top. Now when I distribute over the bottom, 2x times 1 over x, again the x cancels out, and I'm left with 6 over x. And now these same limit rules apply. So as long as the denominator isn't going to 0, then I can take the limit of the top and bottom. And the denominator isn't going to 0. This term goes to 0, right? But you still have the 2 here. So the denominator would be going to 2. So I could take the limit of the top and the bottom, and then I could just take the limit of the two terms, right? Because I can split up over a limit up over a sum and difference. So really what happens here then is that this is going to 0, this is going to 0, and so 5 minus 0 is just 5, 2 plus 0 is just 2, and what I get here is 5 halves, and that would be my limit as x goes to infinity. Now I want to bring in something, because the section in the textbook brings this in, is that this is a rational function, and I don't know how much you remember about rational functions, but this will have a vertical asymptote when the denominator is equal to 0. So if I set 2x plus 6 equal to 0, okay, and then solve for x, so I get 2x is equal to negative 6, so x is equal to negative 3. That would mean when I graph this equation, here at negative 3, you would have this vertical asymptote, okay? And so the function would be going off into infinity there. So given it would have that vertical asymptote given that there wasn't a factor in top to cancel it out. And in this case, there's not. Okay, well, a function can also have a horizontal asymptote. So, for example, y equals 1 over x has a horizontal asymptote of the x-axis. So, and that you can think of the x-axis as y equals 0, right? And so it's leveling off at that asymptote, okay? So whenever the denominator is bigger than, whenever the degree of the denominator is bigger than the degree of the numerator, then the rational function is going to level off at 0, okay? And it would make the limit as you go to infinity equal to 0, okay? So, but if they're the same here, if they're the same degrees, like in this case, so 5x minus 1, 2x plus 6, they both have a degree of 1, then what I do here is I'm going to have a horizontal asymptote. And it's going to be y equals, it's going to be a horizontal line, y equals to a constant. And the constant is going to be the ratio of these two leading coefficients. So it'll be 5 halves. And this will be a horizontal asymptote. Okay, so if I do 1, 2, 3, 5 halves would be like right here. This would be like y equals 5 halves. And if you actually graph this function, it would look something like this. Okay, and this would be a vertical asymptote. This would be a horizontal asymptote. And what you see as you go off into infinity, this graph gets closer and closer to 5 halves. And so that's why the limit is 5 halves. So with these rational functions, the limit is actually equal to the horizontal, the value of the y value of that horizontal asymptote. Okay? So let's look at a couple more here. Let's use that same principle where in the same technique here, and the technique was I'm going to divide the numerator and denominator by the highest degree by 1 over the highest degree of the denominator. So the denominator, the highest degree is x squared. So I'm going to multiply the top and bottom by 1 over x squared. 1 over x squared. And so let's see what happens when I do this. So the limit as x goes to infinity here. Okay, if I distribute 1 over x squared, one of the x's cancel out here, and I'm left with 2 over x. And then this would just be minus 1 over x squared. And then I'll do the same for the bottom. This will be 1. This will be 3 over x. And this will be 2 over x squared. Okay? And again, if I go to infinity, this is not going to 0, so I can just take the limits of the top and bottom here using my limit rules. And both of these go to 0, so it's like 0 minus 0, right? And then this would be, these two go to 0, so I'd get 1 plus 0 plus 0. And this whole limit is 0. See that? We got 0. But notice also this is a rational function where the degree of the denominator is bigger than the degree of the numerator. And so it'll have that horizontal asymptote of y equals 0. It'll level off at the x-axis. So this actually fits with that. In fact, this actually shows you why you have a horizontal asymptote. This actually shows you why you have the horizontal asymptote at 0, or when you have the degrees the same. This shows you why the asymptote is the ratio of the leading coefficients, because when you divide, Okay, the leading coefficients are the only ones that aren't going to be divided by an x. Okay, and so all the other ones will go to 0, and you'll be left with the ratio of the leading coefficients. Okay, so now let's look at this one here. Let's use our rules, and so the denominator is an x squared, so let's divide both top and bottom by 1 over x squared. Okay, so now we get a limit as x goes to negative infinity, and then this is going to, the x squared on bottom is going to cancel out, leaving you with just x, and this will be minus 2 over x squared. And then distributing this over, we get 1 minus 5 over x plus 6 over x squared. Right? So you have this. Now notice, okay, we can take the limit of the top and bottom. As x here goes to negative infinity, this will go to negative infinity, and this will go to 0. Right? And then both of these will go to 0. You'd have like negative infinity. You can think of this as negative infinity minus 0 over 1 minus 0 plus 0, right? This whole thing is going to negative infinity, okay? And this fits with rational functions because the degree of the numerator is bigger than the degree of the denominator. It means that there's no horizontal asymptote. If you graph this, you're going to find that there's actually an oblique asymptote, a linear equation, where it's going to approach. It's going to get closer and closer to that linear equation, but that linear equation is going to negative infinity. And so whenever the degree of the numerator is only 1 more than the degree of the denominator, you get that oblique asymptote. Otherwise, if this were like x to the 5th and this were x squared, then this thing would be approaching a cubic. It'd be the difference in the degrees, and then you wouldn't notice any sort of asymptote, oblique, horizontal, or otherwise. It would just be a curve. Okay? So let's do a couple more here using the technique that we've learned, but now these are not rational functions. A rational function is one polynomial divided by another polynomial. So these are other things. These have roots here. Okay? And so what I'm going to do is use the same technique. And so what I'm going to do is I'm going to multiply the top and bottom by the biggest degree of the denominator. And the biggest degree is actually the x. X to the first is bigger than x to the 2/3. So I'm going to multiply the top and bottom by 1 over x. Okay? And so now I get the limit as x goes to negative infinity, it looks like, negative infinity. And this is actually x to the 1/3, and when I divide it by 1 over x, okay, I'm going to have 1/3 minus 1, and this will actually be x to the negative 2/3. This will be minus just 5, and this will be 3 over x. And what about this one? So then if I divide here, or multiply through, this is just going to be 2. And then this is x to the 2/3 minus 1/3. So this will just be x to the positive 1/3. Oh, nope, to the negative 1/3, I'm sorry. Because you have 2/3 minus 1. And then this will be 4 over x. Okay? And maybe this will be easier to see then. And you'll have to work with these exponents here. I kind of skipped steps there. So there's some exponent rules of exponents going on there. Negative exponents and fractional exponents. I'm taking it for granted that you know it. The book that we're using here actually didn't hit exponents or exponential functions or logarithms very well in the beginning, which I think is unfortunate. That's something that would have been good to look at. So maybe that is something we could look at if it would be helpful to people. So I'm sure you can find a lot of stuff on YouTube about it. But okay, so now so this would be like 1 over x to the 2/3 minus 5 plus 3 over x, and then this would be 2 plus 1 over x to the 1/3 minus 4 over x. And the point here is that this would go to 0, okay, because the x to the 2/3 will keep increasing. Not as fast as 1 over x, but it'll still keep increasing. And then we got minus 5, and then this would go to 0. And this would go to 2. This would be 0. And this would go to 0. And so we'd have negative 5/2. And that would be the limit for that one. Okay? And it ends up being, in a sense, both of these have a degree of 1. That's the highest degree in the numerator and denominator, and it was the ratio of the two leading coefficients, wasn't it? Kind of like a rational function. So, okay, now this one has a root here, but we can use the laws of limits like we've already been using. And what I'm going to do is I'm going to multiply by the highest degree in the denominator. Okay, so it's an x squared underneath the radical, and if you took the square root of x squared, it would just be x, right? So what I'm going to do is I'm going to multiply the top and bottom here by 1 over x, and this would be 1 over x. Okay, so now when I do this is limit as x goes to infinity. And so when I do this, when I distribute that, that just gives you 1 minus 3 over x. Now this, I could write that. We could actually put this over a square root and put a square there, and it would be the same thing. And then I could combine the square roots, and then I could distribute the 1 over x squared over both of those. And if I did that, I would get 4 plus 25 over x squared. Okay, now I could go to infinity. The denominator's not going to 0, right? And so if I went to infinity, this would go to 1 minus 0. And then I could do the limit inside the root as long as this is positive, and this will always be positive, and we're going to positive infinity. So this will go to 4 and that'll go to 0. So square root of 4 plus 0. So it looks like this is equal to 1 over the square root of 4, and that would be 1/2. And so that would be the limit in that case. Okay, so this is, oh, I have one more here. Oh, I got 2 more. Okay, well, let's try these. Now this one is not a rational function, and as you go to infinity, this goes to infinity and this goes to infinity. They both go to infinity, but when you have infinity minus infinity, they say that's undetermined. Or it's indeterminate, meaning it's not always going to be infinity or 0 or finite. It could be any of the 3. So when you subtract 2 infinities, you might get an infinity, or if you subtract 2 infinities, you might get 0, or if you subtract 2 infinities, you might get a finite number. Okay, you could get different possibilities. So if I want to take this limit here, I got to figure something out. And what we're going to do is we're going to use that conjugate rule that we learned for the difference quotients. So I'm going to take x plus the square root of x squared plus 16, x plus the square root of x squared plus 16. Okay, I'm going to multiply the top and bottom by that. So then I get the limit as x goes to infinity. And when I multiply these two, I'm going to get the x squared minus this thing squared, which will just be x squared plus 16, like that. And then on the bottom I will get all of that, x plus square root of x squared plus 16. Okay, then when I distribute this over here, I'm going to get the limit as x goes to infinity, and I'm going to distribute that. The x squares are going to cancel out, and I'll be left with negative 16 on the top. and then I have this on the bottom. Okay, now what I can do, I can multiply the top and bottom by 1 over x, and I could do all of that. But if this is a constant, right, and this is actually increasing, then when you go to infinity, this is going to go to 0. So in this case, when you go to infinity, the difference of these two is actually equal to 0. So this is an example where the difference in infinities go to 0. Okay? And then this is an interesting one, x over sine of 1 over x. And if you remember, sine of 1 over x is where it oscillated up and down forever as you zoom in on 0. You just zoom in more and more, it oscillates more and more. Okay? But the thing in this case is we're not going to 0, we're going to infinity. Right? And so if you go to infinity, then sine of 1 over x is actually going to 0, and that's equal to 0. Okay, this is going to infinity, this is going to 0. So now the question is, well, what's going to happen here? This is going to infinity, that's going to 0. Which one's going to win out? Well, this is a really interesting example here. So what I'm going to do is I'm going to let x equal 1 over t. And if I do that, well, and then let me also do this. This would mean that t is equal to 1 over x. Move the t up there, bring the x there. And notice as x goes to infinity, what does t go to? It goes to 0, right? So what I can do is I can change my limit to t, but I got to change this. As x goes to infinity, t goes to 0. Okay? And then the x here is equal to 1 over t. So I make that 1 over t. And then the sine of 1 over x here will be the sine of t, right? And so I get sine of t. And so this actually is the limit as t goes to 0 of sine of t over t. And this was the limit that we showed in when we did the squeeze theorem and we proved that really important limit. If you remember, the sine, as t goes to 0, the sine of t over t actually goes to 1. And so this limit goes to 1 as well. Okay? Has the same behavior. So this goes to infinity, that goes to 0, but they do it kind of at the same rate, and the product goes to 1. Okay? So again, if you have an infinity times a 0, it's indeterminate. It could have gone to 0, it could have gone to 1, it could have gone to infinity. Okay, it could have gone to 0, a finite value, or to infinity. In this case, it went to a finite value. Okay, so that's a nice example. Okay, well these are all limits as x goes to infinity. So now let's talk about limits that actually go to infinity. Okay, and so if we're going to start with this one here, okay, if you remember, this was the original rational function, and we had a vertical asymptote when 2x plus 6 is equal to 0. That's when x is equal to -3. And this was a vertical asymptote. Okay, and then this had the horizontal asymptote at 2 halves. So like right here, y equals, I'm sorry, not 2 halves, 5 halves. At 5 halves, 2 halves would be 1, right? Okay, so this function looked like this, and then this was kind of looked like that. Okay, and so as you approach -3 from the positive side, so as you're approaching here, the graph is going off into infinity. Okay, and so what we would say is that this limit is equal to -infinity, because it's actually going down. It's going down to -infinity. Okay, so limits that go to infinity are these places where vertical asymptotes occur. Okay, and you're going to get, technically we said a limit doesn't exist because there's no number, right? that this approaches. It just keeps going and going. Okay? And so technically, there's not a limit. The limit doesn't exist, but we can say, in a sense, as you approach -3 from the positive side, your function is going to -infinity. And this is how we could write it. Now, notice here, if I approach from the negative side, I would be going up to positive infinity. So I could write x as you approach -3 from the negative side, right, of 5x minus 1 over 2x plus 6, and this would equal positive infinity. Okay? And so these one-sided limits would exist. Okay? So as you approach -3 from the positive side, you go to -infinity. As you approach from the negative side, you go to positive infinity. And so what we would say is the limit as x goes to -3, just the regular limit here, this does not exist. And why is that? As you come towards -3 from both directions, you're not approaching the same infinity, right? There's rational functions where these would both go down like this, and in that case we would say that this limit was -infinity, or if they both went up like this, we would say the regular limit was positive infinity. But if they go in two different directions, the regular limit does not exist, but the one-sided limits would be -infinity and infinity. Okay? So now, I think your book did a nice job. It had a whole bunch of examples just to show you that a lot of different things can happen. Okay? And so, I want to just think the asymptotes here. Okay? So, the asymptotes are when the denominator is equal to 0. So this denominator is going to equal 0 when x squared minus 4 is equal to 0. So that would be when x plus 2 times x minus 2 is equal to 0. So when x is equal to -2 or x is equal to +2, this is when you can have a vertical asymptote. But when I actually factor these, the top here, this would be the limit as x approaches 2, right? The top would be x minus 2, x minus 2. The bottom would be x plus 2, x minus 2. And you see that one of these would cancel out, and you would get the limit as x goes to 2 of x minus 2 over x plus 2. And in this case, when you plug in the 2, you don't have a problem. You would actually get 0 over 4, which is just 0. So this actually does have a limit, because because that factor canceled out, there's actually not a vertical asymptote at that point. Okay? And so you actually have a hole in the graph is what you would have. And you could actually, as you're watching the video, you could pause and graph these on your calculator. And I might do some of these, okay? But I think that's good for that one, because we've seen that already. So now, what about this one here? Well, this is very similar to the one up above. You would have the limit as x approaches 2, but now you only have one factor of x minus 2, right? And then this would be x plus 2, x minus 2. And then these would cancel out, and you would be left with 1 over x plus 2. Oops, sorry, I should have the limit as x approaches infinity, right? And then as x, sorry, let me just erase this. And what I should have here is this is equal to the limit as x approaches 2 of 1 over x plus 2. And then when you can plug in 2 here, you're given 1/4, right? So in this case, this had a limit of 1/4, right? So this had a limit of 0, that has a limit of 1/4. Well, what about this one here? Well, let's look. We have the limit as x goes to 2, and this is a one-sided limit, so x goes to 2 from the negative side, And here we have x minus 3 on top, and this will be x plus 2 and x minus 2. And what we see here is that the factor, the x minus 2 factor, does not cancel out. So you actually do get a vertical asymptote. And so what I could do here, I'm going to just graph it. So it's going to be infinity here. And you're actually, I think you're going to go to, because this will be, and this will be 2. So I think it's going to be negative infinity, okay? Because this will be negative on top, and this will be positive on bottom. But let's make sure. And so you can always use the graph to do these. So x minus 3 divided by, I'll have x squared minus 4. I'll do a standard window. And yes, as we approach, oh, wait, nope, I was wrong. As we approach 2 from the negative side, this goes to positive infinity. Okay? This goes to positive infinity. So how could you have seen that without the graph? Well, let me try this again. If I approach 2 from the negative side, the x values here are going to be less than 2, and this will be negative. Okay, and then if I approach from the negative side, oh, I see, I wasn't thinking about this term. This will be, if I approach 2 from the negative side, this will be positive, but this will be negative. And I'll get a negative over a negative here, which makes it a positive infinity. Okay, but then this one here is actually, this is approaching 2 from the positive side, and then I get positive infinity. I'm sorry, negative infinity. So as I approach from the positive side going down, I get negative infinity, right? Negative infinity. And you could see it here that this, if you approach from the positive side, this would be negative, and this would be something bigger than 2, which would make that bigger than 4, so that would be positive. Okay? So a negative over a positive is negative. So then, what this is saying here is, what's the limit as x equals 2? Well, the limit as x equals 2, well, as I come from this side, it's going off to positive infinity. As I go to this side, it's going to negative infinity. And so it's not approaching the same thing. So in this case, the limit itself, the normal limit, does not exist. Okay? So the one-sided limits exist, but the regular limit does not exist. And then here's just a couple more. So this is similar to the other one, okay? But this is not a one-sided limit, okay? But notice this is now x minus 2 cubed. And let me actually show you, we can actually simplify this. Limit as x goes to 2, and then I could commute these around, and I would have the opposite of x minus 2. So if I distribute that and commute, I would get this. And then here, this would be x minus 2 times x minus 2, right? And then this would cancel out one of those, and you'd be left with negative 1 over x minus x minus 2. And so then, as you go to, well, let's look at it. I was going to say, as you go to 2 from the positive side, this will be a negative, that'll be positive. And as you go from the negative side, oh, is this a cubed? Ah, sorry, this is a cubed. That's what, because I was confused, because I was thinking that, so there should be another one here, x minus 2. That's a cubed. I was thinking that this limit was going to exist. And it is, because this will cancel out one of those, then you're still left with the square here. So let me actually erase this, and I'll erase all of this. Okay, that was a cubed here, so this is a limit as x approaches 2. This will be the opposite of x minus 2. And now you got 3 of these. So you got x minus 2, x minus 2, x minus 2. There we go. And then this will cancel out one of them, and you're left with the limit as x goes to 2 of negative 1 over, and now you still have 2 factors of this. And now notice as you go from the positive side and the negative side, as you approach 2, this will go to 0, okay, but it's going to go, this will be positive, so in either case it's going to go to negative infinity. So this is one of those graphs here at 2. You have this vertical asymptote, and then this thing is going to be going down to negative infinity on both sides. So this is negative infinity. And let's actually look at the graph and see that that is indeed the case. Okay, so I got 2 minus x. Oops. Let's see here. Let me go back. So 2 minus x divided by x minus 2 raised to the third, and then I'm going to do a standard window. So here it's coming and it goes down. So you see both ways it goes to negative infinity. So here both one-sided limits go to negative infinity. So if I approach from the negative side, it goes to negative infinity. I approach from the positive side, it goes to negative infinity. And so the actual limit, which considers both sides, is negative infinity, and it exists. Okay? And then I just threw these in just to show you that you could do these sort of things with the trig functions. And basically, tangent, if you remember, it has vertical asymptotes here at all these pi's over 2. And so the function actually looks like this, right? And then this would be like 3 pi over 2. This would be pi. And then it kind of does it again. Right? This would be another one. This would be another one. And so if you notice here, this is actually asking you to take a limit at the asymptote. Right? So this is the take the limit as x approaches pi over 2, but do it from the negative side, and then what you see here is you get positive infinity. Now if you do it from the positive side, what do you get? You get negative infinity. And so if you were to say here, does the limit as x approaches pi over 2 of tangent of x, does that exist? No, because it's approaching 2 different infinities. Okay? And so those are limits that go to infinity. So you have limits as x approaches infinity and limits that go to infinity. So, and those are limits involving infinity. So go back, watch the video, count how many times I say infinity, and it'll probably be not quite an infinite number of times, but it'll be pretty large. So, and that's all the stuff we're going to do for limits here.